Welcome to my constraint satisfaction exercise solution. In this problem, we try and answer questions on a multiple choice test. These questions are about a particular Pokemon game. And here we know some of the information about our Pokemons. We can constrain the domain by knowing that number 1 cannot be D, 2, 3, and 4 cannot have A and E, and 5 cannot have D or E. So here's our constrained domain. Next, we're going to need to draw the constraint graph. And let me share that with you. So if you haven't solved that yet, go ahead and solve the constraint graph and pause the video. So here's the constraint graph. We know that the heaviest Pokemon cannot be the slowest. So the heaviest cannot, the fastest Pokemon cannot be the slowest. So the fastest Pokemon cannot be the slowest. There's our not equal constraint. So the dashed lines is a not equal constraint, and the solid lines are an equal constraint. So in other words, answer 4 and 1 are going to have a different answer. All right, we know that the heaviest Pokemon is the slowest. The heaviest Pokemon is the slowest, so there we have an equal constraint. The shortest Pokemon is neither the heaviest nor the fastest. The shortest is not the heaviest and not the fastest, so those are unequal constraints. And finally, the footprint belongs to the fastest Pokemon. So there we go. And here are our domains. These are the domains for each of the variables. So, which Pokemon is the most constrained? If you look at the number of constraints that come into each variable, you can see that variable 4 has 3 constraints, whereas 5 only has 1 and the others have 2. So the most constrained variable is variable 4. All right, so now let's start our figuring out the answers to our questions by using constraint satisfaction. So here I'm going to use both depth first search and depth first search with forward checking. Let's start out with depth first search, and the order of evaluation for our depth first search is going to be just numeric: 1, 2, 3, 4, and 5. And so here's our little root node where we're going to start, and the possibilities are all the values for 1, which are A, B, C, or E. And we'll start with A, and then we'll look at all the values in B to see if they can meet this constraint, B, C, or D. Well, this is an equal constraint, and since there's no value in the domain of number 2 that is A, we're going to end up backtracking on each of these. So okay, so now we're backtracking to B, and from B, again, we have B, C, and D. So they have to be the same. So B looks like a good choice. Let me finish drawing my lines. I may have to backtrack here later. All right, so we know now that these have to be different for 3. And again, we have B, C, and D to choose from. So if we get to B, we'll have to backtrack there because they are equal and they need to be different. So we'll pick C. All right, so C, what is 4? 4 is B, C, D, 2. B, C, D. So these have to be different. So if we go to B, that appears to work. But, so at 4, it has to be the same as 5 and different from 1. So we can see that 1, we've already assigned B, so that won't work. If we assign C to number 4, we see that won't work because then it will be the same as 3. What about D? So let's see. So if we pick D, we'll turn out we're going to have to backtrack from 5 because they have to be the same, and we don't have D in the domain. Okay, so now we're backtracking all the way back up to 3 and D. So let's see. So again, B, C, and D. So for 4, so we know they have to be different from 3. We have D at 3 currently, and so that would make 4. B could work there, but again, we're going to have to backtrack because we have B selected for number 1. How about C? C seems to work. So let's try C. And we have in A, B, and C and 5's domain. So A won't work. It's not the same. B won't work. It's not equal to 4 either. Finally, C does work. Cool. So it looks like we have a solution. What is that solution? Well, let's read off these values. B for 1. B for 2, that makes sense because they should be equal. What about 3? 3 is D. D is different from 2. That's okay. So good so far. Then we have C for 4. Okay, C for 4. C is different from B for 1. That looks good. And finally, C for 5. That looks good because it's the same as 4. So I think we have a solution, and so for this solution, 1, 2, 3, 4, 5, just to make sure it's clear, B for 1, B for 2, D for 3, C for 4 and 5. Okay, so now let's see what depth first search plus forward checking gives us. Basically, all we're doing with forward checking is after each assignment, we eliminate incompatible values from neighboring domains. Basically, this cleans up any contradictions. So we really end up, this step is sort of null and void because it won't happen anymore. And in this case, we're going to try something else. We're going to use, we're going to start at, or from, I should say, the most constrained variable. So if we get that out of the way first, our solution turns out will be a lot easier. And more efficient. We won't have to expand as many nodes and do as much evaluation. Okay, well, let's see what our tree looks like over here. So now we're starting from number 4, and we're going to evaluate basically in the order, reverse order of constraints. So most constraints first, and then 1, 2, and 3 all have 2 constraints, and finally 5 has 1 constraint. So 4, we have B, C, and D. So let's pick B. And if we pick B, then we're going to select B. We would have to eliminate it from here, and eliminate it from there, and eliminate it from here. Okay. So we've eliminated B because of forward checking from 5, 1, and 3, because they're all adjacent to node 4. All right, so domain, now for 1, we have A, C, E. Well, let's try A. So if we try A, and we do our forward checking, which eliminates all the variables that are inconsistent, we would have to delete all these variables from number 2. because nothing is consistent with A. They're all different and we need to be the same. So we're going to have to backtrack there. So we're going to backtrack through C. C, if we choose C, that's great. Then we would eliminate B and D because they can't satisfy the equal constraint. So great, we'll just have C then. For 2, we will go to C. And because we chose C here, and this must be different, we can't have C in the domain of 3. So basically, 3 boils down to D. And finally, 5. We have, let's see, at 4 we have B. And so, yeah, if I selected B here, and actually I did this incorrectly. If I select B here and they have to be equal, that means I eliminate the ones that are different. So that only left B for the domain of number 5. So in this solution, so this was DFS, and here's DFS plus FC. And I get B, oh wait, no, that's number 4. So here, in this case, I get B for 4, B for 5, 1 is C, 2 is C, 3 is D. Does this work? So let's see. And over here we can, let's see, so CC, C, C, D, B, 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 B. Okay, so let's work through the constraints. These are the same, C and C, that works. C and D are different. D and B are different. B and C are different. And B and B are the same. So here are 2 solutions. We found one through depth first search. We found another through depth first search plus forward checking. We can see this tree is this is a much skinnier tree. We did a lot less work here than we had to do with just depth first search. Anyway, thanks for watching, and I hope you got something out of the video. Cheers.